So here's our pre-cal exam review video, and we're going to start with some solve problems here. These are logarithmic equations. Remember that if we start an equation that we're solving and it has an e in it, that your answer will be in terms of a natural log. And I'm guessing that I probably should have set that equal to 0, so we'll start with that. So these are the ones that we learned to look at that middle term, and that middle term tells you what your substitution should be. So let's let u equal e to the x. So if u equals e to the x, then what we're really going to have here, e to the 2x, remember, means the same thing as e to the x squared. So 2e to the 2x, we'll just let that be 2u squared. And then here, this is 5u, this is 3, and that is 0. So now you can see that this is just a simple quadratic equation that we can factor. So 2u, 3, 1u, there's 6, there's 1. 6 minus 1 is going to give us 5. We need the 6 to be positive and the 1 to be negative. So this allows us to see that 2u minus 1 equals 0, therefore u equals 1/2. U plus 3 equals 0, u equals negative 3. But remember, u equals e to the x. So we'll bring our u values over and plug in the e to the x wherever we see u. So e to the x equals 1/2, or e to the x equals negative 3. Now, of course, e to the x can't be negative because there's no power of e that is negative. So this is an extraneous solution. But here, this is a real solution. E to the x equals 1/2. So what power of e equals 1/2? Well, we can find that by taking the natural log of both sides. The natural log of e is 1. X equals ln of 1/2. Ln 1/2 is the solution. Next, log x minus 1/2 x log x plus 4 equals 1. So in order for us to solve a logarithmic equation, we have to have a 1-to-1 comparison. Right now, we've got two logs set equal to a whole number, so we can't use this yet. First, we've got to use properties of logs to condense those two terms. Since this is a minus, we will change that to a quotient. So we have the log of x over, and of course we can Superman this power back, and that becomes x plus 4 to the 1/2 equals 1. Now recall, if we do not see a log base, it's understood to be log 10. So 10 to the first power equals the argument of the logarithm. So 10 equals x over, and I'm going to go ahead and change this back to a radical, the square root of x plus 4. So from here, we don't have any more logarithms, but we do have two fractions set equal to each other, which will allow us to cross multiply. I'll bring it right up here to the right. So 10 square root x plus 4 equals x. So this is turned into a nice little radical equation. We need to isolate that radical and square both sides. And we'll just square it with 100, or with a 10 in front. It's going to turn into 100. So this is going to turn into 100 times x plus 4 equals x squared. And after we square both sides, it's just become a quadratic equation. So 100x plus 400 equals x squared. So I'm going to keep my x squared positive, so 0 equals x squared minus 100x plus 400. So now we've got this quadratic equation, and I just made a quick list of factors of 400, and not a one of those adds up to 100. So what that's kind of telling me is that we need to use the quadratic formula here. So this one's turning out to be a little messy. So x equals the opposite of b plus or minus the square root of 100 squared. 100 squared is 10,000 minus 4 times a times c all over 2a, which is 2. So here's what we've got. I'm going to go to my handy dandy calculator. So that is 100 squared, which is 10,000, minus 4 times 400, which gives us 8,400, which is not a perfect square. So we've got 100 plus 8,400 under the radical, all over 2. But 8,400 is divisible by 400. So we are going to get 100 plus, so 400 is the perfect square. So if we take 8,400 and divide it by 400, dun, dun, dun. Let's try to hope. Look, see if you can see the calculator, but maybe not. So it's 400 times 21. So that means that 20 is coming out. 21 will remain all over 2. So now we can cancel the 2 with the 100 and the 20 and get a final answer here, which I will squeeze on the paper right down here. 50 plus or minus 10 root 21. So we got to go back and we got to look at the original problem. The original problem had log of x and log of x plus 4. So our domain is limited here. Our domain has to be bigger than 0. So domain restriction bigger than 0. So we just need to check right down here. Is 50 minus 10 times square root 21, is that still bigger than 0? Well, the square root of 20 is going to be a little bit bigger than 4. So let's check it out. So 21 square root is 4.58, and 10 times 4.58 is going to be 45.8. So 50 minus 45.8 is okay. So actually, both of those answers are legitimate because both of these answers, if we look at their decimal approximations, are bigger than 0. So those are our answers. So that turned out to be a good problem because we had to condense the logarithms and use the quadratic formula there in solving a radical equation. Next, we're moving on to find the asymptotes. We talked a good bit about them in class. Here's a quick summation. In our function g here, the expression in the numerator is a lesser degree than that of the denominator, which tells me that the horizontal asymptote will be y equals 0. That is always true. And our denominator, x plus 3, is going to yield a vertical asymptote at x equals negative 3. So that's a very, very simple one. Next, letter B, the h function. In the h function, the degree of the numerator and the denominator are the same. So if that's the case, all you need to do are compare the first two terms with division, because that's what the fraction bar means, division. So 3x squared divided by x squared is simply y equals 3. A horizontal asymptote at y equals 3. Now, to find the vertical asymptote, let's do the division here. Or better yet, let's factor, excuse me. So if we factor the numerator, we end up with 3x, x, and I know it's factorial because 3 and 7 and 4 are all related. So let's put a 7 here and a 1 here and minus plus. There's 3, there's negative 7. 3 minus 7 is where we're getting the negative 4 from. X, 1, 2 plus 1 and negative 2. There's negative 2, and there's positive 1. So what we see here is that we've got a factor that's going to cancel. Fantastic. If the factor cancels, that's telling us that we have a hole or a point of discontinuity in the function. So in order to find that hole, we're going to take our restricted value, so x cannot equal negative 1, and what we're going to do with that is plug it back into the simplified function with substitution. So if my simplified function h is h of x equals 3x minus 7 over x minus 2, take that restricted value and evaluate the function. Which gives us negative 3 minus 7, which is negative 10 over negative 3. So my location of my hole is at negative 1 and 10/3. Remember, if you're giving me a location, I'm expecting an x and a y. And then go back to that simplified function, and it'll tell us where we're having our vertical asymptote. Our vertical asymptote is going to be at x equals negative 2. So this particular function has it all. It's got a horizontal asymptote, and we can see it even again there. If it's the same degree, cover up everything except for the first two terms and divide, because that's what the fraction bar represents. Horizontal asymptote at y equals 3, a hole at negative 1 10/3, and a vertical asymptote at x equals 2. Lastly, if the numerator is a higher degree than the denominator, that indicates that we will have a slant asymptote. And how do we find it? We divide, because that's what the fraction bar is intending for us to do. So if we do long division here, and really we could just do synthetic, but I'll be wrong. We're going to find the quotient. That's what we're after. The slant asymptote is the quotient, not the remainder, but the quotient. So let's find the quotient here. So x goes into 2x squared. 2x times x is 2x squared. 2x times 3 plus 6x. So that is negative 4x minus 3. X goes into negative 4x, negative 4 times. And really, I can just stop here. The remainder is 9, but the remainder is irrelevant in terms of the actual asymptote. I need the quotient. So my slant asymptote is at y equals 2x minus 4. And then, since nothing's going to cancel here, I will also have a vertical asymptote at x equals negative 3. So that is a quick reminder about asymptotes and how to find them. Next, given the zeros, write a function of least degree. So note that I'm giving you 1, 2, 3 factors here, or 3 zeros. But remember, i's always come in pairs. So 1, 2, 3, 4. We are going to have a 4th degree polynomial when we finish with this function. So first we have x equals 3. If x equals 3, that's coming from the factor x minus 3. Next we have 5, so x minus 5. And then 2 minus I root 3. So if x equals 2 minus I root 3, let's use inverse operations in order to determine this quadratic factor that it will yield. So x minus 2 equals negative I root 3. Let's square both sides. So x squared minus 4x plus 4 equals I squared times root 3 squared, which is root 9, which is 3. So this right-hand side is just going to become negative 1 times 3, which is negative 3, which we will add to both sides to yield a quadratic factor of x squared minus 4x plus 7. Now, on our exam, you will not be using your calculator for this, so you need to push through and multiply. So let's start with the first two factors. X minus 3 times x minus 5 is x squared minus 8x plus 15. We'll use the distributive property. And now we're going to power through and use the distributive property 3 times here. X squared times x squared is x to the 4th minus 4x cubed plus 7x squared. Take the negative 8x through. So negative 8x cubed plus 32x squared minus 56x. Next, positive 15x squared minus 60x. And then 15 times 7 is 70 plus 35, so plus 105. Add all of our columns, and we get our polynomial that is our answer. So x to the 4th minus 12x cubed, excuse me, 7 plus 32 is 39 plus 49 plus 5 plus 54x squared minus 116x plus 105. This is a polynomial of least degree that has these particular given zeros. Next, find the zeros, justify your answers. We will be using our calculator in order to do this. So the first thing we need to do is we need to graph the function. And I will zoom in so hopefully you can see everything. So there's the function, still showing it on the screen. We go to our y equals screen, and we are going to graph this function. So y equals 3x raised to the 5th minus 9x raised to the 4th minus 15x raised to the 3rd plus 15x squared minus 18x plus 24. So when we graph this function, we can already see that we have a 0 at negative 2, we have a 0 at positive 1, and 1, 2, 3, we have a 0 at 3. So we're able to see 3 of the zeros. 3 of the zeros are real, which is indicating that the remaining 2 are most likely imaginary, and we'll just have to use a quadratic solving strategy in order to find those. So negative 2, positive 1, positive 3. Those are our zeros. So I'm going to write those down. X equals negative 2, positive 1, and 3. Now what we're going to do in order to justify your answers, rather than just telling me they're on the calculator, you're going to show me this with synthetic division. So we're going to start with negative 2, and we are going to divide. And in order to justify your answers, you're proving to me that this is indeed a 0, because we should be getting a remainder of 0 when we divide by that 0, negative 2. So bring down the 3, that's negative 6. Remember, when we use synthetic division, we're multiplying and adding. And it checks on the first one. And when we divide by that first 0, it depresses our polynomial down 1 degree. So we went from a 5th degree polynomial to a 4th degree polynomial, and we're going to divide by the next 0, which is 1. And we depress the polynomial down again to 0. Now we're going to divide by the remaining real root that we found, which is 3. And I'm going to check my work here. If I'm kidding. When I divided, it's because I can't count. 1, 2, 3, 4. It's not 3, it's at 4. So let's go back and change that. Not positive 3, but 4. And let's just get rid of all that. I still need that, so I'm going to bring it down. 3, negative 12, 3, and a negative 12. And I am dividing by 4, which, if I'm looking at those numbers, I probably could have factored it more quickly than doing this, but that's okay. That's 12, that's 0, that's 0, that's 3, that's 12, and that is 0. And that's what I'm looking for. I'm looking for a remainder of 0. And this remains a final quadratic polynomial that I'm going to set equal to 0, which is 3x squared plus 3 equals 0. Now when I solve this, first thing I'm going to do is dump the 3's. X squared plus 1 equals 0. X squared equals negative 1 square root. X equals plus or minus I. So that means getting rid of that 3 that I mistakenly put there. That is a positive I and a negative I. 1, 2, 3, 4, 5. 5 zeros. I was after 5. 1, 2, 3 of them are real and 2 of them are imaginary. Last two problems here are graphs, and wanted to remind everybody that we will be discussing circles on our exam, and you need to be able to graph a circle, and you also have to be able to write a circle in a standard form from an expanded form, and that of course includes completing the square. But let's quickly graph this. So if our standard form of a circle is x minus h squared plus y minus k squared equals r squared, we see here that our center point is at negative 3, positive 1, and my radius is 4. So if we're going to graph it, it's pretty simple. Plot the center back 3, up 1, and then the radius is 4. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and here is where our circle would be. So you must know this for the exam. You have to know the standard form because you have to be able to take an equation that is in expanded form and take it to standard form by completing the square. FYI. Last problem here is a piecewise function. You need to be able to graph and interpret a piecewise function. So first of all, I'm going to draw in some auxiliary lines giving me some boundaries, and those are happening at negative 2 and positive 2. Remember, these lines are auxiliary and they should be drawn dashed because they're not technically part of the graph. They're just giving us some guidelines, just like asymptotes do. So now we've got 3 pieces. So here is the first piece of the domain where we're going to be working, and it's going to be for the first function. I'll do that one in blue. So when x is strictly less than negative 2, we're going to be dealing with the linear function negative 2x. So if you want to make a little xy chart, you can totally do that, and we can plot a couple of points here. So how about negative 4 and negative 3? So when x is negative 4, y is equal to negative 4 times negative 2, which is positive 8. So we are back 4, up 8. And if we have a slope of negative 2, we're really just going to be going down 2 over 1, which we'll see here. When we plug in negative 3, we get positive 6, down 2 over 1, down 2 over 1. I'm going to leave that circle open because this piece of the function is where we are strictly less than negative 2. So there is going to be my first piece of my function. So let it be good. Next, second piece, it's just a constant function. A constant function of positive 3 existing in the second middle slice of the domain here, which exists between negative 2 and positive 2. And it will be closed here because our function needs to not have any breaks in the domain, and then open on the other side. Constant function y equals 3. That's a horizontal line. Lastly, to the right of positive 2, everything strictly greater than or equal to positive 2 is a linear function 1/2 x. So maybe we do a few points here. So let's put in 4, let's put in 6. I'm choosing even numbers since I've got to divide them by 2. Half of 4 is 2, half of 6 is 3. So over 4, up 2, over 6, up 3. And if our slope is 1/2, let's go down 1, back 2, and we can put a solid point there. That is what our piecewise function should look like, given 3 separate slices of the domain, thus 3 branches of the graph.